lesson on applied optimization problems. And we're going to do a lot of examples. It's going to take a while, but I think you're going to see some actual use to some of the techniques that we've been kind of going over in this section on applications of differentiation or derivatives. So I'm going to start off with this first one, right? And this first one is talking about maximizing the area of a garden. So the figure is very helpful. You'll notice that we have a rock wall on one side, so we don't need to worry about any wire fencing on that side, but we do need to have wire fencing on the other three sides. So they've gone ahead and told us that we're going to use the letter X to represent the sides that are perpendicular to the rock wall side, and the letter Y is the side that is parallel or across from the side of the rock wall. Now, we want to maximize the area in terms of this garden, but we can't just keep using infinite number of or larger dimensions for the fencing, because we do have a constraint. All right, and that constraint is that we only have 100 feet of wire fencing. So the first thing I'm going to do is write down my area formula, all right, which is going to be length times width. So in this case, X times Y. All right, so that's the area for this garden. Okay. However, when I look at that, you'll notice that we have a constraint that deals with the total amount of wire fencing in feet. And so that's where I'm going to think of the perimeter, all right, which is adding up all the sides, the side lengths around the rectangle, all right? But in this case, you'll notice a little different. We have two of the X ones, right, with two X's, but we only have one Y that we need to worry about, all right, because ultimately the rock wall is going to serve as one of our other sides. So we only have to worry about one side length for Y. And this has to be equal to 100. Okay. So what I did here is the next step is to isolate Y. All right. So Y equals 100 minus 2X, moving 2X over. And now I'm going to substitute this letter Y, which equals 100 minus 2X, into this letter Y. So I'm going to rewrite my area as a new function that is now X times 100 minus 2X, or 100X minus 2X squared. Okay, I'm going to pause here because this is ultimately the area function that I want to maximize. So I'm going to find the maximum on this of this function using some of the strategies we used in earlier lessons. But before I do that, I just want to take a moment and you want to think about what your possible values for X could be. All right, so think back to the very beginning of this problem where we said we had 100 feet of total fencing. All right, so if I make X equal to 20, right? So 20 times 2 is 40. 100 minus 40, Y is 60 feet. Okay, so the idea is that whatever you make Y and whatever you make X, right, they're going to have to balance off each other to make this equation true. So you can't just say, oh, X is 1,000, right, because that won't make any sense. Because they need to be positive numbers, right? We can't have negative lengths of fence, right? We can't have an X value that's greater than 50. If our X value was 51, then our Y value would be a negative. So we can't have an X value that's greater than 50. And if I use ultimately for my Y values, I don't want to have a number that's greater than, I think, 25, because ultimately if we do something larger than that, then our X would have to be end up being too large as well. Okay, so just keep that in mind before you kind of do the strategy here. So I'm going to write down the area function. All right, it was 100X minus 2X squared. So what I'm going to do is I'm going to take the derivative of that. Okay, so that's going to be 100 minus 4X. All right, and that means we're going to have our critical points. We're going to have we're going to have our critical points are going to make it equal to 0. Nothing's going to make this undefined. I should have said that I want to find the maximum of this area function on the bounded interval between 0 and 50. That was the whole point of that discussion about the possible X values. Can't have an X value more than 50, otherwise our Y value would be negative. So if I plug in my endpoints, let me do that actually first real quick. So let's plug in the endpoints. I'll do the derivative here in a second. So if I plug in my endpoints, I get 100 times 0 minus 2 times 0 squared. That's going to be 0. This is I got 100 times 50 minus 2 times 50 squared. All right. I don't actually know what that is, but if you plug in a calculator, you end up getting 0 as well. All right, so both of the endpoints happen to be 0. It doesn't matter that they're the same, but now I care about finding the critical values, which is going to be that derivative again, 100 minus 4x, set it equal to 0. Okay, 100 equals 4x, or x equals 25. So an x value of 25 would maximize the garden area, all right, and keep us in the constraints of that we only have 100 feet of wiring to use. All right, it also says what is the area. So I'm going to plug in 25 into the area function. All right, and then you can go to Desmos or find that it's 1,250 square feet. All right, now I left this other slide here blank because I'm going to show you what happens when you sketch it. All right, I'm going to go to Desmos and sketch this area function, 100x minus 2x squared. All right, so we have 100x minus 2x squared. All right, I'm going to make a table. That way I can zoom fit. And we care about, let me get the zoom there. There we go. Okay, so we care about having our highest y value is 50. There we go. And then we also need to have 25 in there, right? That is our, there we go. That's our maximum. So you'll notice we have 0, 50. Those are the endpoints. And we said our critical point was 25. And that is where we have our highest y value of 1,250 square feet. All right, so you can see how Desmos allows you to find this as well. But ultimately, I want you to focus on finding the critical points, not just using the Desmos. Okay, so ultimately, Desmos, just if you want to put a sketch, you can. But I left this slide here blank in case you wanted to sketch it. Okay, so that's it for the first one. I'm going to move into some more optimization problems focused on this problem-solving strategy. Okay, so for this next question, we're going to be talking about maximizing the volume of a box. So if an open-top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side, what size square should be cut out of each corner to get a box with the maximum volume? So I'm going to draw two things. First thing I'm going to draw is our cardboard box that we're using. So we have 24 inches by 36 inches. And then I'm going to draw what's going to happen when you actually cut out these little tiny squares in each corner, which I'll label with X by X, right? Their lengths, side lengths will be the same. All right, so I'm going to draw, let's see, we'll have, again, doesn't need to be like a great drawing here, but the idea is that we're going to be having a box that's being cut out here. So we'll have, let me actually draw it a different way because that might be a little confusing. So give me 1 second. Let me make sure I know how I want to draw this. Okay, so let me try it like this. So I'm going to draw these together, something like that. Okay, I think that's, well, I'll go with that. Not very good, but this is my height. This is my width, so 24 minus 2x inches, and my length is 36 minus 2x inches. Very similar to my my width. All right, and ultimately this is about maximizing the volume. So the first thing I'm going to do is write down the volume, which is length times width times height. So this is going to be 36 minus 2x inches times 24 minus 2x inches times the height, which is whatever height we choose for the squares that we're cutting out. Okay, now I'm going to multiply this all out over here on this side. All right, so that's going to be 36 times 24. Definitely need a calculator for this. So 36 times 24 is 864. Okay, then 36 times negative 2x is negative 72x. Negative 2x times 48 is negative 2x times 24 is negative 48x. Then we have positive 4x squared. Now that's not everything because we need to multiply that by x. Let me simplify first. So 864 minus, 72 plus 48 is 120 plus 4x squared and then times x. So I'm going to get, let me write in standard form, 4x cubed minus 120x squared plus 864x. So this is my equation for volume, all right? And ultimately, when I look at kind of that discussion that we had with the previous problem, before I find the critical points, I want to think about what's going to be my interval here in terms of what I'm looking at for my values of x, because I can't just make x whatever I want. Excuse me. So in this case, if you think about it, right, the width is 24 inches. So if I cut out 1 inch, 2 inch, 3 inch squares, whatever I end up cutting, but if I cut more than half of it, right, if I cut 13 inches, then I don't have enough material on the backside, right, to have the same amount of cardboard cut out, right? So I have to have less than 12. So when I look at, in terms of my bounded interval, I'm going to be looking at between 0 and 12, all right? So I'm going to start out by plugging in the endpoints, right? So plug in 0. Obviously, that's going to be 0. Plug in 12. So that's going to be 4 times 12 cubed minus 120 times 12 squared plus 864 times 12. Now, I'm going to do it on my phone next to me real quick, but you know, with a lot of these, it'll end up being 0, but you should take the time to see if it actually will be 0. So that's going to be 12 cubed times 4 minus 120 times 144 and then plus 864 times 12 and you get 0. Okay, so also getting 0 means that when I look at the sketch of this over this bounded interval, then I'm looking for the absolute maximum between x values of 0 and 12. So I'm going to take the derivative. Okay, so my derivative of volume is going to be 12x squared minus 240x plus 864. Okay? Now, you may not see this, but you can actually divide all three of these numbers by 12. So I'm going to write down my derivative is 12 times x squared, 240 divided by 12 is 20. And then 864 divided by 12 is 72. Now, unfortunately, there are not factors of 72 that add to negative 20. So you would have to either use the quadratic formula or you could complete the square. Just because I absolutely love completing the square, I'm going to. So I'm going to move this over, get negative 72. Oh my gosh, it's been so many years since you've done this. So you have b over 2 squared, which is going to be negative 10 squared, which is 100. So I'm going to add 100 to both sides. This is going to factor to x minus 10 squared. Negative 72 plus 100 is going to be 28. Take the square root of both sides. Get x minus 10 equals plus or minus the square root of 28. So x equals, we'll do a little reducing here, 10 plus or minus, there is a perfect square in 28, 4 times 7, plus or minus 2 square root of 7. Now, ultimately, when you get the decimals here for this, you've got two approximations. So let me get them for you. So we have 2 times the square root of 7. So the square root of 7 times 2 plus 10 is 15.292. And then if I do the other one, 10 minus 2 times the square root of 7, you get approximately 4.708. Now, you'll notice before I did this that I said I wanted to look on the interval between 0 and 12. Where did I put that? Right here, right? Between values for x between 0 and 12. When you look at these two critical values, only this one is between 0 and 12. So I actually am not going to be looking at evaluating this volume at the 15 point something one. So I'm going to plug in that my value. All right, so 4.708. So that's going to be, I think it was 4x cubed. Yep, 4x cubed. So 4 times 4.708 cubed minus 120 times 4.708 squared. I think it was plus 864x. Yes, plus 864 times 4.708. All right, so whatever that is will give me my maximum volume. All right, I'm going to go to Desmos to find that answer and just show you how a lot of this stuff you can confirm with your graph on Desmos, which is super nice. All right, so I'm going to type in, still use this one, 4x cubed minus 120x squared. There we go. And then plus 864x. Make a table if you would like. So you can zoom in. Not going to want to zoom in there because my x value is, I'll say 5. Because I care about the one that's at 4. I can zoom over and kind of see what's happening between 0 and 12 is my max. Look at there. Okay. So if I look at my maximum, it's right here. You already know the x value is 4.708, right? We found that approximation. So here is my maximum volume at that side length of square that's cut out of this cardboard box, 1,825.297. And it's going to be cubic feet, I believe. Is this in feet? I'm not sure. Inches, cubic inches, my bad. So it's going to be 1,825.297 cubic inches. So this is my maximum volume using that side length. Okay, so that's it for this one. I'm going to move on to the next one. Okay, so for the next one, we're going to talk about this problem where we're trying to minimize travel time. So we have critical points. So hopefully you see the connection between those two things.